In the previous lecture, we saw that physics and data-driven can be integrated. The next question is how? How does physics influence the learning processes? Physics-informed neural network provide one implementation of physics-informed learning. The network learns from data. Its predictions are also tested against the governing equations. Any physical inconsistency is penalized during training. Learning becomes a constraint optimization problem. Consider a simple mass spring system. Its motion is governed by a simple differential equations. The system evolves according to physical parameters, including mass, damping, and stiffness. Now, assume only a few measurements are available. A conventional neural network learns from those observations. Within the observed region, the prediction is accurate. Beyond the observed region, it quickly loses reliability. A physics-informed neural network extends the training objective. The network learns from the observations. The governing equations become part of the optimization. Physics continues to guide the solution where measurements are unavailable. The predicted trajectory remains physically consistent beyond the observed region. The same strategy scales to complex physical systems. The model first learns general degradation behavior from historical datasets. It's then refined using limited data from a new system. Only the system-specific parameters are updated, and this enables long-term prediction. Digital twins can also estimate quantities that cannot be measured directly. Instead of adding new sensors, they can be estimated from signals that are already available. Physics defines the relationship between measured signals and hidden system states. A learning model performs this inference. This is virtual sensing. Hidden parameters reveal information about system design. Interpretable learning shows how each parameter influences performance. Some parameters dominate system behavior. These become the priorities for design. Digital twins transform prediction into design intelligence. These examples illustrate what digital twins can already do. The next step is to extend these capabilities. Several challenges remain. Strongly coupled partial differential equations still limit computational efficiency. High-dimensional systems require more scalable learning. Reliable integration of physics and observations is equally important. These challenges are driving the next generation of digital twins. Models will become adaptive. They will continue evolving with the system. Learning will span the entire life cycle. Knowledge generated during design, testing, deployment, and operation will become part of the same learning process. The final step is closing the loop. Digital twins will connect digital understanding with physical execution. The repository contains a simplified physics-informed neural network implementation used in this lecture. Explore how it works, modify the model, extend it to your own problem. See you in the next lecture.